Howdy, cosmologists. Welcome back to the channel. Today's lecture is entitled Lighting the Worlds. What I will be talking about in this lecture is what exactly matter is composed of, and what exactly, or how exactly, do we classify or describe light. This is the first of two lectures on the subject. We will be talking all the way up to blackbody spectra, and then I will be talking about what exactly a blackbody spectrum is and what the implications of those spectra are in terms of understanding the fundamental characteristics of astrophysical objects. So, without further ado, here's a lecture. I hope you enjoy.
Okay, I guess we can get started. Let me stop sharing my screen for a moment. There we go. Howdy, y'all. I want to apologize for being behind the schedule, and I am far more behind the schedule than I intended to be. One of the reasons for that is because I was a bit overambitious in terms of the changes that I could make to courses over the course of this, or during this semester. Instead of trying the inverted class with but one of my classes, I tried to do it with three. And so that's far more work than I intended. So what I'm going to do is I'm going to move this towards a more traditional lecture setting where I will be giving the lectures on or during the scheduled time. They are recorded. So I will then edit the recording to make it more condensed and then post that onto YouTube for folks that aren't here. Let's see. During the course of not today, but during the course of the lectures, there will be in-class quiz questions. I do plan on keeping that aspect of the course. So before, if you read the syllabus, the idea was that I would give questions at the very beginning, essentially to make sure that you're keeping up with the material. Now I'm going to intersperse those questions within the lecture itself. So that, again, basically to make sure that you all are paying attention and understanding the material as we go through. The other thing I want to talk about the other two things I want to talk about are the project topics. I believe in the course schedule, the topics are due Friday, although it might be saying that it's due today, but I'm extending that to Friday. What I plan on doing is creating a Google Doc with all of your names, and then what I would ask is this doc would be shared amongst all of you. What I would ask is that you put in, sometime before Friday, put in the title or the subject matter for the topic that you want to write your term paper on. The caveat to that is that your term paper cannot be of the same topic as you're debating. So, for example, if you're part of the geocentric heliocentric debate, then your term paper cannot be on either of those two subjects. It must be on something else dealing with cosmology. In terms of the debate, I know a couple of you have been wondering about that. Again, the debates will be held at the end of the semester, essentially one per class. And so the geocentric heliocentric debate will be first. The steady state Big Bang will be held second, and then the final debate will be between weakly interactive and massive particles in terms of dark matter. Now, hopefully each of your groups is 6 members. If it's not, then please let me know. I will be double checking that in the coming weeks to make sure that folks or each of the groups is adequately represented, because what's going to happen is the debate style is going to be one of the two sides is going to go first. And then one group member will introduce the topic. They will have 5 minutes to introduce the topic. Then it will switch over to the other group. The one member of the group will introduce their topic, and then it's going to go back and forth with each member essentially taking 1 point that they want to give. So if you look at one side of the debate, you'll have a person who introduces the topic. You will have 4 points that you want to raise to promote what your side is, each given by a different member of your group, and then the last person will follow it up with a conclusion summarizing all of the points that have been made prior to this. And it's going to be, and so the debate will be an interweaving between the two groups. Introduction, point one, point two, and so forth and so on down the line. I will write all of that up and post that to Blackboard at some point in the coming couple weeks. So just to have, so you can have something that's basically a summary sheet that you can work on when you are planning your debates. Are there any questions about that? All right. As always, I recommend that you get together with your groups earlier rather than later. That way that you have plenty of time to organize, plenty of time to divvy up responsibilities and cover the responsibilities of any members that aren't fulfilling their obligations, as is going to happen with any group project, unfortunately. So yeah, we have that. I do want to plug one thing. Tonight we have a public event. We do public events every couple weeks called Evening Under the Stars. And unfortunately tonight the weather is looking not great, so it'll be closed dome. We will be highlighting images, most likely those images taken by Owen. We will be highlighting images that we have taken using our observatory, and basically just showing off what we can do with the telescope using a digital camera. And the other reason why I'm hawking this is because I will be giving the public talk. The public lecture, the way the public night is structured is that the first 45 minutes is a talk given by a guest speaker. Moi will be the guest speaker. And that's followed up by 45 minutes of highlighting the telescope. And so the topic that I will be discussing is women in astronomy. I will be highlighting women who have made key observations or key advances within the astronomical field. So that is the topic du jour. All right. In terms of the topic du jour today, in terms of the class, let me share my screen. Actually, let me see if, yes, that's open. Let me check Discord real quick. Okay, it seems to be all right. Doesn't seem to be any fires coming off there. So hopefully you can all see Lighting the World. Please let me know if you can't see it. So what we're going to be discussing today are, hopefully I can get through all the slides. If not, then we'll split this into 2 lectures. What we're going to be talking about today is essentially light. We're going to be talking about the properties of light and the properties of matter that allow us to do what we do in astronomy. As I like to say, 95%, and that's really kind of a made-up number, but it's to illustrate that the vast majority of the knowledge that we have in astronomy is due to the collection, analysis, and understanding of light. As you might imagine, we can't do very much in the lab. We can't pull Jupiter into a laboratory setting and manipulate Jupiter so that we can figure out its fundamental properties. All we can do is study the light from Jupiter and its surroundings to allow us to even get just the most fundamental idea of what Jupiter is, such as its mass, its radius, how fast it's spinning, so forth and so on. If we want to know more detail about Jupiter, we have to get more creative. And in some cases, we actually have to send satellites or probes out to Jupiter to do much more detailed studies of Jupiter based on just simply distance. The closer you get to an object, the easier it is to see, the more data that you can collect. And so today we're going to be talking about what exactly light is, what are its properties, what exactly matter is, what are its properties, and how the two interact so that we can get some of those fundamental characteristics that I was talking about. Let's see. Aha, I can do this. So what is matter? Well, matter is typically composed of three, I guess, large-ish objects. These are your baryonic and baryons and leptons. Baryons come in two flavors. They come in protons and neutrons. And so when you look at the atom itself, which is the principal component of all matter, what you have is a nucleus, which is composed of protons and neutrons. Those protons and neutrons are then subdivided. Oddly enough, atom comes from the Greek meaning indivisible, but as it turns out, the atom is in fact divisible, at least once. The proton and neutron are created through the collection of quarks, which I'll go into very briefly in a moment. So you have neutrons and protons, which are roughly the same mass. Neutrons are a little bit more massive, but they get their names because neutrons are neutrally charged. They have no overall charge. Protons are positively charged. Now, electrons, I hesitate to use the word orbit. Electrons surround the nucleus of the atom. We will be looking at what is known as the Bohr model of the atom, which describes the electrons as orbiting around the nucleus, very much in analogy to the planets going around the sun, with a couple of different caveats. What we find actually using quantum mechanical methods or quantum mechanical understanding is that the electron actually is within a cloud, a probability cloud. Because of Heisenberg's uncertainty principle, which states you cannot both know the location and speed of an object, the more you understand the location, the less you understand the velocity. And so we can primarily measure the velocities of these electrons as they whiz around the proton, which means that we don't really know where it is at any particular moment, which is why it's a probability cloud. All we can say is that the electron is more than likely in this area surrounding the nucleus. And the more electrons you add to the situation, the larger the clouds get, which to fill those electrons, or to occupy, or to the occupied space of all of those electrons. We'll get more into what that means momentarily. But the takeaway points here are that the indivisible parts, or the indivisible parts of matter, are composed of what we call baryons, which are quarks, and leptons, which are the electron, the muon, and the tau, basically tau electron. And then you have neutrino counterparts. Neutrinos, which we'll go into later on and are vital for our understanding of dark matter, particularly so for those of you who are on the dark matter debate, you really want to pay attention to what neutrinos are. And I've just lost my train of thought with that. So neutrinos come in three different flavors. There's the electron neutrino, there's the muon neutrino, and there's the tau neutrino. Really, those are just, those particles simply result from the decay process of electrons, muons, and tau. That whole concept is beyond the scope of this. But just know that neutrinos, the reason why there are three flavors is because they are produced via radioactive decay of electrons, muons, and tau particles. Now, when it comes to quarks, They are separated into basically 6 components, and they have to do with in the direction of spin that they occupy. There's up, down, charm, strange, top, and bottom. What do those names mean? Nothing really. They were basically came up with as, or they were basically derived as kind of a joke, because they were like, how do we name these things? And so one of the PIs who was in fact responsible for finding these quarks said, why not up, down, top, bottom? And then when they found 2 more, they were like, charm and strange? I don't know. So I suppose there is some sort of rationale behind where they came up with those names, but from a physical standpoint, they don't really mean much. And kind of going to skip over that. And so this is basically illustrating what we're talking about in terms of radioactive decay. There is decay that will what's called beta decay, where part of a neutron will actually just spontaneously decay into a proton, an electron, and a neutrino. And depending on what type of electron gets emitted, that's going to correspond to what kind of neutrino gets emitted. This is what we refer to as a weak interaction, which also is why neutrinos are referred to as weakly interacting particles, because they result from basically a weak interaction which created them. And then beyond that, the only thing that they really contribute, or the only way that they really interact with matter, is via gravitation, because they do have a minute amount of energy. And occasionally, very occasionally, which we'll go into in a moment, very occasionally they will interact with particular elements and cause a slightly energetic event, or basically a flash. Neutrinos can be found in a number of different places. You have neutrinos from the Earth, which come from just basically natural radioactive decay, not only from neutron decay that decays into a proton, but for example, potassium-40 will decay into either, I believe it's sodium, but also argon. I may be very wrong about the sodium. For some reason, I'm blanking on that. But the key one is argon. When potassium decays into argon, it will actually emit neutrinos in that process. And so certain radioactive decay, like uranium into lead, those will also produce neutrinos. We also can produce neutrinos in particle accelerators. When we're studying subatomic particles, essentially the collisions that occur can also produce neutrinos. Now, as I like to, the analogy I particularly like in terms of subatomic particles, or at least particle accelerators, is the idea that we have a Swiss watch, and you want to know how that thing works. So the best idea, or the best way that we have come up with for figuring out how that watch works, is by taking another watch and then throwing them at each other at very high rates of speed. They smash, and then we look at the gears which pop off from that collision. That's essentially what a particle accelerator does. It accelerates small particles like protons and neutrons, smashes them together, and then looks at the resultant particles from when they break apart. Then you have astrophysical neutrinos. You have neutrinos due to the nuclear processes within the sun, also within stars. You have atmospheric neutrinos, which occur when some cosmic rays will slam into a muon, and that will create, the cosmic ray will slam into the atmosphere, which will create a muon and a neutrino, a muon neutrino. And then finally, you have remnants of the Big Bang. The Big Bang was obviously a very energetic event, and when it started cooling off, there was a lot of radioactive or nuclear reactions when things started to recombine and actually form matter. During that process, a lot of neutrinos were produced. And a lot of those neutrinos, because they are weakly interacting, they have been able to survive for 13.7 billion years because they just simply whiz by most of whatever is in front of their way. So, in terms of detecting these neutrinos, I'll go into in a moment, but essentially you need a very, very large vat of gallium with tons of gallium in this sphere, and every so often, every couple of days or so, you might get one interaction with a neutrino with a gallium atom. To give you an idea of just how many neutrinos are passing through us, the Earth receives about 40 billion neutrinos per second per centimeter squared from the sun. That's not including Big Bang or other astrophysical phenomenon. About 10 or 100 times that is coming through us from a Big Bang. So right now you have billions upon billions of neutrinos going through your body right now that affect you not at all. So that's, for me, that's kind of really weird to think about. Just how many subatomic particles are actually streaming through my body at the moment, and I have no knowledge of it. My body really has no knowledge of it because there's nothing in my body really that's going to interact with neutrinos. And even that many neutrinos, the total mass of that is still almost negligible. In comparison to this, neutrinos outnumber protons by the order of 8 orders of magnitude or more. So neutrinos, when it comes to the total number density of objects within the universe, we are vastly outnumbered by neutrinos. It's very much like thinking about bacteria with relation to humans. While there are billions of humans on the Earth, there are hundreds of billions of individual bacteria roaming around our surface. So, in a sense, it's very much in that sort of analogy, in terms of there is a vast wealth of neutrinos within the universe that are streaming through it in comparison to what we would consider ordinary matter, which is why neutrinos are believed to be the leading candidate for why there is dark matter. While each individual neutrino has, basically, we have not been able to determine the mass of neutrino because we haven't gotten instruments precise enough to measure something that small. We've been able to determine that they do in fact have mass, and we've put upper limits to it. But even given a basically negligible amount of mass per neutrino, because there are just so many of them, then we believe that might be the leading candidate for dark matter. Like I said, neutrinos don't do much while passing through matter, and that's really an overstatement in the fact that they basically do nothing. They do cause a small shift in gravitation, but again, at that scale, with neutrinos passing through your body, that is pretty much negligible. The amount of force between a neutrino and your body is not even worth mentioning. So, like I said, it is very difficult to observe them, but occasionally you can. And so, occasionally, when a neutrino actually smacks into, for instance, gallium, for example, then you're going to get a small sort of pop where it's energetic enough that light will stream off, but also subatomic particles will stream off, either an electron, a muon, or a tau. Now, one of the problems that we had in the late 90s, early 2000s, what was referred to as the solar neutrino problem, is that we had models of what the nuclear reactions within the sun were. And so from those models, we could accurately predict the size of the sun, we could predict its luminosity, its radius, or its mass, things of that nature. But the problem was those models also predicted we should have a certain amount of neutrino generation within that, within those reactions, those nuclear reactions. And at the time, the detectors were getting only about were only detecting about 1/3 of the neutrinos that were generated, that we predicted to be generated. And the reason for that is because we hadn't quite figured out that muon neutrinos and tau neutrinos were a thing, and we're only detecting, we're only set up to detect electron neutrinos. Now, the fun thing that neutrinos also like to do is they like to change flavor spontaneously. So while an electron neutrino might first come out of the sun, it could spontaneously turn into a muon neutrino in the 8 minutes it takes to get to the Earth. So neutrinos are fun that way. They just like to basically change shape or change orientation, as it were. Now, like I said, this is an example of the Kamake 1. I believe that's the Kamake 1 was the first Japanese detector, and the Japanese really are leading the way in terms of neutrino detection. So they have a lot of used up mines, mines as in stuff you take ore out of. And so they put these detectors deep underground in order to minimize the amount of background radiation or background noise that they would get within this. And so the first detector basically wasn't filled with gallium, but was filled with heavy water. Heavy water being, instead of just a normal hydrogen atom bonded to two hydrogen atoms bonded to oxygen atom, it was two deuterium atoms, which is a particular isotope of hydrogen, bonded to an oxygen atom. And neutrinos can interact with that. We have subsequently made improvements. The Kamake 2, for example, is vastly larger than this particular model, to the point that you can actually sail a boat inside the sphere. And they actually have to use boats in order to get to the various detectors that are surrounding it, because hopefully you can see these little white dots or little white things that are on the side. All of those are individual cameras, because they are designed that once there is light, once there's that flash from that neutrino, that light gets picked up by those cameras, and that allows the scientists to narrow down what is happening, what caused that particular light, where did it come from, and where did the neutrino come from that produced it. And that allows them to determine whether or not the neutrino was in fact a solar neutrino or just some kind of random background neutrino from, say, the Big Bang, or a star, or the atmosphere, or what have you. So let's move on to what actually light is. Now, it was prior to Galileo, the first people to really talk about light were the folks like Newton and Huygens, and there was a debate as to what actually light is. And what Newton was able to do using a prism was that Newton was able to demonstrate that light was not monolithic. So if you had white light, that white light had different colors within it if you were able to spectrally disperse it, which is what a prism does. It takes white light, and because of how refraction works, it splits that light into its components, which we see as the rainbow pattern of color. Newton believed that light was actually composed of what he referred to as corpuscle, or it was corpuscular. They were small packets of light which were streaming through the universe. His arch enemy, Huygens, on the other hand, basically told him, no, light is in fact a wave because of certain experiments that he did that really can only be explained if light acted like a wave, very much like water does. But prior to these two gentlemen, you have Galileo, and Galileo knew that, or at least assumed, that light had some kind of speed. That when you lit a fire, it takes some amount of time for the light emanating from that fire to reach your eye. It's not an instantaneous event, or at least Galileo assumed that this was not an instantaneous event. However, he was not able to actually measure the speed by using what his experiment was to put a poor grad student, or essentially what amounts to a grad student, on a distant hilltop, and he would measure the time. I guess they synchronized hourglasses or synchronized watches and had a pre-set time where the assistant would turn on the lantern, and Galileo would then try to measure the amount of time it took for that light to get to him. But unfortunately, his timepieces were not. One thing, the distance was too short for his timepieces to be accurate enough to measure that change. Now, to give you an idea of the speed, or excuse me, give you an idea of what distance you really need in order to measure this, or at least measure it using the instruments at the time. Around 1676, a Danish astronomer by the name of Romer was studying the Galilean moons around Jupiter. And what he wanted to do was come up with precise periods of these moons in order to determine the mass of Jupiter, at least to a better accuracy than was known before. And he could do that using Newton's revisions of Kepler's laws. Now, as I said, in order to get a better precision of the mass than from previous experiments, he needed to know the periods of these these moons very, very precisely, which meant that he observed these moons for on the order of years. So he constantly made observations of these on the order of years, and he noticed the precision of his timepiece was good enough that he noticed that the period of Io, for example, was quicker when the Earth was closest to Jupiter, and slightly longer when the Earth was further away from Jupiter in its orbit. And he surmised that the reason why there was a difference between those periods was light travel time. It took less time for the light from Io to actually reach us when we were closer together than when we were further away. And so what he did was velocity is equal to distance times time. And so he knew what the time differential between those two periods was. And then he thought he knew what the size of the Earth's orbit was. And then he just simply calculated what multiplied those two together, and he got a speed. Now, he drastically underestimated the speed of light because of the fact that he drastically underestimated the size of the Earth's orbit. But this is kind of for these experiments, for what Galileo was trying to do, this is the distances that he needed to have in order to get a time, in order to basically be able to see this time differential. So it's no wonder that Galileo wasn't able to measure the speed. And so a more modern, the next time that the speed of light was measured and actually got a relatively accurate measurement was Fizeau and Foucault in 1850. And what they did was they took a stationary mirror and they coupled it with a rapidly rotating mirror. And they had a light source, a candle or what have you, and they noted during the rotation of the mirror, when the mirror would flip back and forth, then they can measure the angle they can measure the distance basically from the deflection. now that they have a distance, they can also measure the time it takes for that deflection to occur. For the mirror to be in one position, it moves into another position. There is a slight time lag for when the light appears to shift. Now, for an individual shifting, for an individual turning of the mirror, that time is rather small, probably too small for them to accurately measure. But they made an average. They took lots of measurements. The mirror, like I said, was rapidly rotating, and so they were able to basically just sum all of those experiments together and take the average, and that's how they were able to come up with an accurate value for time. Because again, velocity is equal to distance times time. They could determine the time lag. They could determine the angular distance due to the rotating mirror, and then they got a velocity. And they measured the velocity to be roughly around 300,000 kilometers per second. So speed is, or light is very quick, but it is finite. And what Einstein tells us in relativity, which we'll get into later on, light is the ultimate speed limit. Nothing can travel faster than the speed of light. No information can be received from one part of the universe to another part of the universe faster than light can carry it. Now, the speed of light itself is not invariant. The speed of light will change depending on the medium in which it's propagated, meaning light travels through a vacuum at 300,000 kilometers per second. But light travels through air just slightly less than the vacuum, because the medium is slightly denser. Light travels even slower through water, again because the medium is denser. And there is active research at this point to develop a material through which light stops, that light actually doesn't move at all, because the medium is so dense that the speed of light becomes zero. That to me is pretty wild. But we can actually slow down light to the point that we can literally see a photon moving across a particular substance. And that's one of the ways that we can sort of detect that light can be thought of as a particle. So here is the basic idea that what Newton came up with. If you take white light, pass it through the prism, you get the Pink Floyd cover for Dark Side of the Moon. You get that red light does not refract nearly as much as blue light. And so red light splits off from the rest of the colors. You have red, you have yellow, green, and then blue, or Roy G. Biv. And those colors correspond to the specific wavelength of light. And so if you were to characterize light as a wave, it would be a transverse wave, or what looks to be a sine wave. And the wavelength is the characteristic width of the wave. So if you go from up, down to up, and then back down again, the wavelength would be the length between two particular peaks in that wave. So red is long, blue is short, and that will become more important as we start talking about the colors of astronomical bodies, and more specifically, we talk about the temperatures of astrophysical bodies. So red light has a longer wavelength, blue light has a shorter wavelength. Commensurately, red light carries less energy than blue light. And so what I like to say is that light, regardless of how you characterize it, is the transportation mechanism of energy from point A to point B. And the amount of energy that a particular light particle or wave carries is directly related, or actually inversely related, to its wavelength. And so longer wavelength light carries less energy than higher wavelength light. And we can study, and this is also part of what Newton was doing, we can also study what is known as spectroscopy. And what spectroscopy can do is if you take that array of light that is created by one prism and you pass it through basically a shield that has a slit in it, then you can, and then pass that light through it and then pass it through another prism, you can widen out that particular color and you can separate yellow, for example, into its component wavelengths. And so you can gain a further understanding of, or a more precise understanding of what these wavelengths are. And there are things buried within the spectrum of light that are important for our understandings of fundamental quantities about them. And we'll get into spectra in a moment. This is just showing you the relationship between the velocity and the speed of light and the wavelength. I'm just going to skip over that for a moment. Now, what is light specifically? Really, the take-home point here is that light is tied to electromagnetism. You can think of the light as being composed of both an electric field and a magnetic field. The take-home point that propagates in a particular direction at the speed of light. Take-home point here is that a field contains energy. So that is how light is a container for energy, is because it is composed of these electric and magnetic fields. And so there was a long history of linking electricity and magnetism to light to get to that formal understanding. And that culminated with these Maxwell equations that we see here, that essentially the electric field and the magnetic field are linked together. One causes the other. An electric field or the electricity, which is the movement of negatively charged particles, that the movement of those particles will actually give rise to a magnetic field. Now, if you got a magnetic field from, say, a bar magnet, which is produced differently, and then you brought it closer to, say, a wire, the speed at which if you bring in that bar magnet at a particular speed, that's going to induce electricity in that wire. So the two are interconnected and related to each other. An electric field can create a magnetic field, a magnetic field can create an electric field, and vice versa. And Maxwell was the one who, using these four laws that you see here, was the one who actually was able to unify electricity and magnetism into what we call electromagnetism. Because of Maxwell's equations, and because of other observations that folks made, particularly in the infrared back during, well, actually, I believe it was in the early 1800s, particularly for infrared radiation. When they looked at a particular light source, they were able to detect basically radiation coming off the flame. But when they moved away from the visible part of the spectrum, they still were able to detect energy coming away from it. And that is the infrared part of the spectrum. And so what we define now is, and you can think of it as, wavelength has an infinite range. Wavelength can be infinitely small and infinitely large. We don't know of any physical reason for limiting the wavelength of light. The visible part of the spectrum, basically the wavelength that range from 700 to 400, and that is biologically determined. The visible part of the electromagnetic spectrum, which is the full range of wavelengths, the visible part of the electromagnetic spectrum is based on what we can literally see. And so the average extents of the human eye, the average person can only see wavelengths as small as 400 or as large as 700. But there is a vast amount of energy and a vast amount of radiation beyond that. When we talk about the radiation, the short wavelength radiation, we immediately go to ultraviolet, which we're all fairly familiar with in terms of getting a suntan or potentially cancer, which leads us into the fact that ultraviolet light, X-ray radiation, which you get obviously when you break something, and the gamma ray radiation are exceedingly harmful when in high doses. X-rays, if you just have an X-ray once every so often or once every few years, then the amount of radiation you get from that X-ray is nominal in the sense of a healthcare or a health danger to your health. But if you're an X-ray technician, the reason why they leave the room or wear a heavy lead vest is because if you get exposed to X-rays over and over and over again, basically 40 hours in a work week or more, then you start having to worry a little about little things like cancer. Gamma radiation, again, doesn't turn you into a raging Hulk monster, unfortunately, it just kills you. But thankfully, our atmosphere is almost opaque to ultraviolet and pretty much opaque to X-rays and gamma rays, which is why life is able to exist on this planet. Now, if you go to the longer wavelengths, the first wavelength section after visible is called the infrared part of the spectrum. We most naturally associate infrared with heat. Then you get into microwaves. Then you get into radio waves. Certain stars and galaxies will emit light in all wavelengths. Certain stars, though, will only emit a very, very tiny amount of very, very high energy light and very, very low energy light. When we talk about the temperature of things, we have three different temperature scales. The only one that you the only one we really care about in astronomy is Kelvin, because it's the most physically based of the three. And what I mean by physically based is that there is an absolute zero. There is a starting point. And what absolute zero means is that that object does not move at all. Temperature is linked to the motion of atoms. The hotter something is, the faster the atoms within that object move around, smack into each other, and so forth. When you reach absolute zero, nothing is moving. And so far, we have not actually obtained or observed anything in the universe at absolute zero. Motion seems to be a ubiquitous part of the universe. So while space is cold, it is not absolutely cold. It's around 2.7 degrees, depending if you're in deep, deep space. It's a little bit warmer if you are just hanging outside of the Earth, because the sun actually does a fairly decent job of warming things up. So you can see here various temperatures. Absolute zero, you have the freezing point of water, which is at 273 Kelvin. 373 is boiling. We are around 300 Kelvin. The surface temperature of the sun as compared to that is 5,800, and the core of the sun is around 15 million Kelvin. So if we're 300 Kelvin, then the surface of the sun is on an order of magnitude, or about 10 times larger than we are, or 10 times hotter than we are. And then the core of the sun is incomprehensibly hot. And the sun is actually a rather cool object in terms of astrophysical bodies. Now, when we look at opaque objects or solid objects, what we can see is this relationship between color and energy. When you are welding, say, a metal bar, if at the very beginning, when you apply heat, when the temperature of the bar is relatively cool, the bar will glow a dull red. As you continue to heat the bar and the bar heats up, that color goes from red to orange. And then once you heat it up enough, the bar will turn into a yellowish or whitish color. And then if you manage to heat the metal before it melts, it'll actually turn blue. it'll become white hot or blue. And again, that shows us a relationship between the temperature of something, meaning how much energy it has, and the temperature and the amount of basically the temperature and the energy. The more energy that you put into the object, or the object has, the higher that temperature is going to be. Here's just an example of the fact that, and I'll show you in a moment, what we refer to as a blackbody curve. We emit light, human beings emit light over pretty much all wavelengths. But we emit most of our light in the infrared, which is why when we look at ourselves through the infrared part of the spectrum, we actually glow, like you can see on this image, and it shows basically how well our heat is distributed. So for this individual, there is a lot of heat coming from the head and from the torso, but our limbs are correspondingly or comparatively rather cold, which is why your hands tend to freeze up before your chest does. But we do actually put out light in the visible part of the spectrum. But the reason why we don't glow is because the amount of light we put out in the visible part of the spectrum is so tiny in comparison to the red light. All right, so before we get into, I think at this point I'm going to stop, and we're going to talk about Wien's law, Stefan Boltzmann's law, and what exactly blackbody curves next time. So I will stop sharing my screen and answer any questions that folks have. And again, I will be editing this video to cut out all of the extraneous material and posting this to YouTube sometime later this evening.